Alrighty. So Newton's third law. A force is a push or pull. You might have seen that already. Force or push or pull that acts upon an object as a result of its interaction with another object. Forces result from interactions. I was talking with Austin and William yesterday. There's the one question on that fill in the blank thing about, I don't know, was it this law, Newton's third law? I think it involves how many objects and how many forces. And the right answer is 2 objects, 2 forces. Action, reaction, 2 objects though, right? As discussed in lesson 2, some forces result from contact interactions like normal force, frictional force, tensional force. Applied forces are all examples of contact, and other forces are a result of action at a distance interactions like gravity, electrical, and magnetic forces. Okay? If I want to punch Ken in the face, I have to contact it. Sorry, I keep using this, but you're right there, right? There's contact, right? But if I drop the tennis ball, does it have to be Does it have to be touching the ground for gravity to work? No, it's a non-contact force, and you probably never thought about that before. According to Newton, whenever objects A and B interact with each other, they exert forces upon each other. And those forces are equal and opposite. When you sit in your chair, your body exerts a downward force on the chair, and the chair exerts an upward force on your body. There's the 2 objects, there's the 2 forces. There are 2 forces resulting from this interaction, a force on the chair and a force on your body. These 2 forces are, of course, called action and reaction, and are the subject of Newton's third law. Formally stated, Newton's third law is, and of course there's always different ways to write it. Newton himself probably wrote it in Latin to begin with. Certainly didn't write it in everyday English. For every action force, there is an equal and opposite reaction force. Now, almost everyone, probably from about grade 4 and up, can recite that. If you started it, they can give it back to you. And again, it's do you believe it and do you really understand it? And that's my goal today. This statement means that in every interaction, there is a pair of forces acting on the 2 interacting objects. The size of the force on the first object, once again, equals, I keep repeating it, equals the size of the force on the second object. The direction of the force on the first object, of course, is opposite to the direction of the force in the second, and forces always come in pairs. Blah, 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 blah. Mr. Bennett, just keep repeating yourself. I know. It's kind of part of the job. Here are some examples. Okay, a variety of action-reaction force pairs are evident in nature. That happens all the time. Let's go through some examples. Consider the propulsion of a fish through water. A fish uses its fins to push water backwards. But a push on the water will only serve to accelerate the water because the force is on the water. Right? How do then the fish move forward? Since forces result from mutual interactions, the water must also be pushing the fish forwards, propelling the fish to the water. So push back on the water pushes on the fish. The size of the force in the water equals the size of the force on the fish. They have to be equal, and the direction of the force in the water backwards is opposite to the direction of the force in the fish forward. I think you all get that, right? When I give you a unique situation, will you get it? Hopefully. We'll find out. For every action, there's equal and opposite, blah, 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 repeat, repeat, equal and opposite. We get it, right? We get it. Equal and opposite. Consider the flying motion of birds. A bird flies by use of its wings. The wings of a bird push air downwards. Since forces result from mutual interactions, the air must also be pushing the bird upwards. The size of the force on the air equals the size of the force on the bird, and the direction of the force in the air downwards is opposite the direction of the force in the bird upwards. And that's again, for every action, there's equal in size and opposite in direction. Blah, blah, blah. We get it. Stop repeating. We get it, right? Consider the motion of a car on the way to school. Maybe you rode in one this morning. A car is equipped with wheels that spin. Duh. As the wheels spin, they grip the road and push the road backwards. No, they don't. How does the car push the road backwards? It just does? Does the road move backwards, Josh? If I lean on the counter here and push, does the counter go anywhere? No. But if I'll just go this side so you can see better. Right? But if I wear like rollerblades or something like that, or standing on ice and I push here, I'm going to go this way, right? The counter pushes back on me. How come the counter doesn't go that way? It's bigger than me, and it's attached to the ground, right? There's a lot of friction there, right? Just because you apply force doesn't mean it has to move. I thought forces cause acceleration. There's no net force, right? If there's no net force when I push, like which way's friction when I push? Andrew, are you listening? Because this is the learning part. Here's where you learn all the stuff, right? If I push like this, which way's friction, right? Left. If I just stand like this and don't push it, how come the desk doesn't go flying this way, towards it? Because you just said there was a force going out. How come when I go like this, it doesn't go flying towards it? Friction just stops? Friction only exists when there's a force against it, right? So it's not just going to, that would be really lousy if things just started flying around all over the place because there's no force on it, right? That wouldn't, couldn't have that. We vote those guys out if they allowed that to happen. Okay, so anyway, the wheels push on the road and push the road backwards. Since forces result from mutual interactions, the road must also be pushing the wheels forward. The size of the force on the road equals the size of the force on the wheels, and the directions are opposite. Blah, 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 we get it. Blah, 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 blah. Okay, let's just see if you get it. Come get a clicker. Okay, so, while driving down the road, firefly or mosquito or who cares what, strikes the windshield of the school bus, makes a quite obvious mess in front of the face of the driver. This is a clear case of Newton's third law of motion. The firefly hit the bus, and the bus hit the fireman. Which of the two forces is greater? The force on the firefly, force on the bus, they are the same, or we need more info. Sing the Jeopardy song in your head and answer the question. In your head, which of the two forces is greater? The force on the firefly, the force on the bus, they're the same, or I need more info. No, it just gives me a note that someone has a question. Okay, Braden, here's the chance to show me what you know. Don't listen to anyone else, think yourself. Do I go to the next question? Yes, I did. No, I just stopped this one. Okay, let's just see. Is this like democracy where you vote, kind of? Maybe we should just vote by clicker. Wouldn't that be a whole lot easier? Well, I'm pleased to see that the majority of you got the right answer. I am not so pleased that some of you got it wrong. What does Newton say? For every action force there is a, what's that word? Equal. Have we not been talking about that for 3 days? Equal means the same. They are the same. How come the bug gets schmucked and the bus does not get schmucked? The bus is a whole lot bigger. F equals m, little tiny m, right? If the force is the same, little tiny m is going to mean big giant acceleration. Living creatures don't like accelerations. Same size force, giant bus means little tiny acceleration. Buses don't care about little tiny accelerations. They don't get schmucked. When buses run into trees or rocks or bridges, they get schmucked. Big forces. Equal. There it is there. You guys have that? No, you don't. Trick question. That's not a trick. I've been telling it to you over and over and over again. I guess I gotta repeat myself more. Equal. Every action there is an equal. See, equal. Do you think I'm gonna ask it again? Yeah. The fact that the butterfly spatters only means that it has a smaller mass, less able to withstand the larger acceleration resulting from the interaction. Besides, fireflies have guts, and bug guts have a tendency to be splatterable. Windshields don't have guts. You know the old saying, it's not the fall that'll kill you, it's the landing?
It's like the sudden stop.
The sudden stop, yeah. Does that mean you should go ahead and jump off buildings? No. Okay. Think critically now. Think. Don't listen to your neighbor unless you think they're right. For years, space travel was believed to be impossible because there was nothing that rockets could push off in space in order to provide the propulsion necessary to accelerate. Because we need things to push off, right? To get going. This inability of a rocket to provide propulsion is because space is void of air, it's a vacuum, so the rockets have nothing to push off of. Gravity is absent in space. Space is void of air, so there is no air resistance in space. Or nonsense, rockets do accelerate in space and have been able to do this for a long time. Think. This might take a minute or so. I'm going to go do my attendance. Who said D? Well done, Brody. Buy yourself a cookie at lunch. You deserve it. Did those guys try to discourage you?
I didn't ask them.
You didn't ask them. Excellent. All right, my friends. Do rockets accelerate? Of course they do. Have you not seen the video? Of course they do. Are there air molecules in space? Oh, it's a vacuum. Okay? Space is void of air, that's true. So the rockets have nothing to push off of? That really doesn't matter. Gravity is absent in space, is that true? Yeah, which is probably why most people picked it. What does that have to do with it? Nothing, I just knew that was the only one that I agreed with, so I picked that one. It was kind of, very much for that. Space is void of air, so there's no air resistance in space. Is that true? Uh-huh, but that's not the reason. Right? Because all of those are assuming all three of these. This is good practice for university guys because they throw multiple choice questions at you and they throw trick questions at you. This is really good practice. All of these, A, B, and C, are all assuming that rockets don't accelerate. And they're giving you true reasons, but they're not reasons for rockets not accelerating because rockets do accelerate. So the correct answer must be D. Rockets do accelerate in space, and I've been able to do so since the beginning of time. They just didn't have rockets. How do they work? Brody, do you know how they work? No? Yeah, and that's fair enough. It's not that hard to explain, but rocket science, right? Exactly. I actually knew a guy at university. He was studying rocket science. He was really cool at parties, right? What are you studying? Rocket science. Yeah, it's like, fuck.
Cool. It's rocket science.
Yeah, he was a nerd. Worse than me.
I saw it in Cup Street. It was part of it, and it showed this huge ass station.
Yes, right. What happens is they got fuel in the rocket, right? And the rocket burns that fuel, and it actually pushes on the gas molecules. And its conservation of momentum is kind of how it works. So it's creating something to push off of. Right? So you know when you see that rocket, there's a flame part going down? It's not the flame part pushing on the ground that makes the rocket go up. It's the rocket pushing on the particle of the flame that takes off.
Then you should have put that in and not something like that.
Well, I know. Yeah, fair enough. It's a bit of a trick, but it gets me to be able to talk about it. Sometimes it's a good idea to force kids the wrong way, to question, make them think. Okay, so yeah, I'm a bit of a trickster. Fair enough. Here's the answer in the written format. It's a common misconception that rockets are unable to accelerate in space. The fact is that rockets do accelerate. There is indeed nothing for rockets to push off in space, at least nothing which is external to the rocket. But that's no problem for rockets. Rockets are able to accelerate due to the fact that they burn fuel, push the exhaust gases in a direction opposite direction to which they wish to accelerate. If you've seen The Martian, you'll know that part at the end there where they do a little bit of burn to sort of replace the rockets, slow one of them down, I think, right? Or speed them up, I can't remember. It's been a while since I saw the movie. Yeah, because the rocket's going at this speed, and Mark Wahlberg, right? It's going like at this speed, right? And the relative velocities are too much. They can't hit. The force would be too much, so they have to match their speeds, right? It's kind of like driving down the highway on two motorbikes and handing the guy beside you something, right? Can you do that? Yeah, because you're relative speed. Or have you seen like a guy on top of a car and then the plane comes down and they match the speeds and the guy jumps on the plane or something like that, right? As long as the speeds are the same, it's fine. In fact, it's no different than Josh and Alex driving down the highway in the same car. Everything in the car is going at the same speed. It's easy to hand something over. Okay, this one's a little easier. I hope you get this one. Many people are familiar with the fact that a rifle recoils when fired. This recoil is a result of action-reaction force pairs. A gunpowder explosion creates hot gases that expand outward, allowing the rifle to push forward the bullet. Consistent with Newton's third law of motion, the bullet pushes backwards upon the rifle. The acceleration of the recoiling rifle is, okay, so the bullet goes flying forward, rifle goes backward. The acceleration of the recoiling rifle is greater than the acceleration of the bullet, smaller than the acceleration of the bullet, or the same size. You may begin singing. Mr. Bennett, you're such a trickster. The force of the rifle equals the force of the bullet, yet acceleration depends upon both force and mass. The bullet has a greater acceleration due to the fact that it has a smaller mass. Remember, acceleration and mass are inversely proportional. Is there one more? Okay. In the top picture, right there, below, Ted Budget, thank you, I did write it, is pulling upon a rope that is attached to a wall. In the bottom picture, Ken is pulling upon a rope that is attached to an elephant. In each case, the force scale reads 500 newtons. 500, 500. Kent is pulling with more force when the rope is attached to the wall. With more force when the rope is attached to the elephant, the same force in each case. What do you think? More force when it's attached to the wall, more force when it's attached to the elephant. Same force. I was trying to gauge by my voice and my body expressions which one is right. I am adept at not conveying that at all. Pick C, it's always C, right? Multiple choice? Oh, yay! The force scale reads 500. The same. Kent is pulling with 500 newtons of force in each case. The rope transmits the force from Kent to the wall or the elephant and vice versa. Since the force of Kent pulling on the wall and the wall pulling on Kent are action-reaction force pairs, they have equal magnitudes. Inanimate objects such as walls can push and pull. Do it all the time. Try running into that wall at full speed. You'll get a push. Oh, it looks like I got a couple videos to show you. This is okay. So, question number 1: an asteroid travels through space in a straight line forever. Clearly, that would be number 1, right? Number 1 is Newton's 1. Objects in motion stay in motion. I think there's no argument there. Okay, Reese, here's the listening part. You and a friend are on ice skates. You push her, and you both move in opposite directions. 3. Yes, action, reaction. That one, they start you off with a couple easy ones. You drop your books in the hall while running. The books slide down the hall until they slow to a stop. Laura says 1. Who wants to agree? Does anyone want to disagree? 1? You say 2. Why 2, Bailey?
Because eventually it does have to stop, which means another force is acting upon it.
I won't disagree with that. I think it's kind of both, right? Objects in rest or objects in motion do stay in motion unless acted upon by an outside force. So that's why the books slow down. And because there's that outside force, that kind of brings into this one here. There is a force which causes acceleration. I'll take 1 or 2, as long as you can explain it. While making a snowman, you make a really big snowball. You push the ball really hard, but it only accelerates a little. 2, just like the crazy guy with the rifle, right? Big mass, small acceleration. Hunters typically get a bruise on the shoulder after firing a shotgun several times. Yeah, 3, action, reaction. Right? Cars driving in the rain can trap water under their tires. You guys know what that means? Or what that's called? Hydroplaning. When the brakes are applied, the car still won't stop. I would say 1, objects in motion stay in motion. You can't stop a car unless you can apply a force. Okay, number 7 is always stupid, and every year I say, okay, I gotta fix that. What do you think they mean here? Friction. Well, all of them, Alex? Explain. Can't? Just hedging your bets. Ladies? 1 and 2? See, I like this one because friction happens, right, when there is, right, it's a reaction to something. So I like 3 for that one. Okay, now my favorite questions that everyone always asks me about. If everyone in the world ran east at the same time, the world would stop spinning. Now, before we get to the logistics and whether we could actually do that, which I will talk about, I promise. Okay? If everyone in the world ran east, right, the world would stop spinning. You say 3, action, reaction? Yes, I would say 3. Okay, now, let's get out our globe here, and let's just talk about this. Which way does the Earth spin? You don't know? Which way does the sun move? Set to the left. Dan's going to be our sun once again, because he's up close here. Okay, so, which way does, if the sun rises in the east, Braden, does the sun really move around? Does the sun really move across the sky? No, we're moving underneath it, right? Okay, so if the sun, let's find Canada, there's North America, right? Where's the east part of North America? Over here. Okay, so there's the sun, it's rising in the east, so we must be spinning this way, right? We're spinning this way. Depends on which side you're looking at it from. Right? Depends on which way you're up. So we're spinning this way. So if you ran east, we're spinning this way. Here's North America. If we ran to the ran to the east, we'd be pushing back this way. So would that slow the Earth down? You bet it would. Would it be enough? The reason I put the world clock up there was because you can put the sun down. It's probably getting hot. There's that many people on Earth, about 7.4 billion. How much does the average person weigh? In kilograms. Well, okay, in pounds, the average person, the average man is probably about 175 average. The average woman probably about I'd say a little less. Let's say 125 for easy figuring, which makes the average person 150. That's easy figuring. We'll say the average person weighs 150 pounds. Convert that to kilos for me. Anyone know? Divide by 2.2. You know what? Let's make it average. You guys listen, because you're not. I can see you're not. Stop talking. Okay? Seriously. This has to end. It has to. If I had more room in this space in this room, you guys would have been moved by now. I don't want to displace someone because I have to move these. But there is a little bit of room here. I've got 3 tables, and I will empty them. Stop visiting and start listening. You can't get through the class without it. Let's say about 75 kilos. So take 7.4 billion, which is 7,400,000. Yeah. One more set of zeros. Times 75. You got it like as a...
That's 5.55 times 10 to the power.
That's about the mass of humanity on the Earth. 5.5 times 10 to the 11 kilos. The mass of the Earth? 5.9 times 10 to the 24. Insignificant. Insignificant, not going to happen. Don't bother trying. I can't even get 30 people to bring a pencil every day. How are you going to get the entire world to run east at the same time? Oh, yeah, not done. Couple more questions. Not done. Relax.
What if we have all the animals in the world?
Maybe. If the world stops spinning, the oceans would spill onto land, killing us all. That is Newton's one. Objects in motion stay in motion because the world oceans would continue in motion. Who would get it first, Vancouver or St. John's? Which way? Yeah, I don't even have to think now. Earth, we're spinning like this. We stop. The oceans keep going like this. Vancouver's going to get it first. We're safe for a while. People in St. John's should start running east. Yeah, like that. Yeah. Last one. A powerful explosion can send small materials flying at very fast speeds. That is 2. Yes. Okay. Thank you for your attention today. We will be drawing 3-body diagrams tomorrow.